Hi all, welcome to the lecture on the introduction of matrices and matrix arithmetic. So today we're going to introduce matrices. So a matrix is an array of real numbers, for us, real numbers with a fixed amount of rows and columns. So each entry is identified by its row position and column position, and the dimension of a matrix is denoted m by n, where m is the number of rows and n is the number of columns. So, as you take higher level math courses, you'll see matrices used in different ways with different elements as part of the array. But right now, we're just going to kind of keep it simple with real numbers. So for this first example here, notice that there are 3 rows. So 1, 2, 3. So we call this one R1, R2, R3. And we also have 3 columns as well. So this could be column 1, column 2, column 3. And the dimension of this matrix is a 3 by 3. If you and another person were looking at the same matrix and that other person asked you, what value is in the first row, second column? You would just go to your first row, you'd go to your second column and be like, oh, it was 4. Row 1, column 2 is 4. And so that's how you locate or identify items in your matrix. So for the next matrix here, we're going to have 1, 2, 3, 4 rows and 2 columns. So this is going to be a 4 by 2 matrix. And then lastly, here we have 2 rows and 1, 2, 3, 4 columns. So this is a 2 by 4 matrix. So there's a couple things that we can do to combine matrices. They are addition and scalar multiplication. So a scalar is just a number. Like, we're not going to multiply it by x or by a function or take the inverse of it or anything. We're just going to multiply it by 1 or -3 or whatever. And adding 2 matrices is what you might expect it to be. So adding a matrix, you just have to add location by location. And multiplying by a scalar multiple is just multiplying each element in the array, in the matrix, by that number. So we'll do some examples here. So for the first one, for 2b, each entry gets multiplied by 2. So we have our original matrix, which is I'm writing this right to left, which is kind of backwards, but just copying down all the entries. And then I have 0, -10, +10, that's off center. And then in my first column, okay, so I'm intentionally kind of leaving a weird space here because what I'm going to do is I'm going to multiply every single one of these terms by 2. So it's going to be 2 times -2, 2 times 0, 2 times -3, right? So all of these 2's, they get sent flying everywhere. And so my resulting matrix then is going to be 2 by -2, which is -4. Then going across in my row, 2 times 0 is 0. And I get -6, and then I'll get 24, -20, -10, and my last row I'll have 2, 20, -2. In the next example, I want to take a scalar multiple of a and then also subtract it, take away b from that. So one thing to notice is that if you are going to add or subtract matrices, they have to be the same size. I didn't have to check that in the first example because it doesn't matter. If I'm multiplying by a scalar, great. I don't care what size my matrix is. Just distribute away, push the 2 all the way through. For example 2, I do care about the size of my matrices because they have to match. So let's quickly go through and identify the dimensions of each matrix. So as before, this one has 3 rows and 3 columns. So this one is a 3 by 3. B is also a 3 by 3. And C is a 2 by 3, 2 rows and 3 columns. So it's clear to us that A and B are going to play nicely together and that C is kind of the odd duck out. So knowing that, we can go ahead and look at what 3A is, and then we're going to subtract B. So first, let's do 3A. So I'm going to write A as I did above, and then from that I'm going to subtract B, and then I'm going to have what everything is, and then hopefully I will have room down here to simplify. Okay, so this is my plan for space. All right, so A, I'm going to go down in the columns. So 1, 2, 3, 4, -2, 1, 2, 3, 4. And that gets multiplied by 3. So I'm going to have 3 times, 3 times, 3 times. For B, I'm not multiplying it by a scalar, so I'm just going to record what was in B. Oh, I think I know what I wanted to do with my space. Okay, so if I'm going to simplify, I'm going to start with just simplifying A. So I'm going to get 3, 12, and 6. 6, -6, and 9. 9, 3, and 12. I apologize in advance for any arithmetic errors that I'm bound to commit. So let me just double check really quick. 3, 6, 9, 12, -6, 3, 6. Okay, and then from that, I'm going to subtract B. So again, we still haven't done really anything to B. We've only multiplied A by 3. So I still have -2, 12, 1, 0, -10, 10, -3, -5, and -1. So I'm going to scroll way over here. So now that I have my 2 matrices, I've pushed my scalar multiple through on A. I'm going to just subtract term by term. So in my first position, I have 3 minus -2. Right? So that comes from here and here. And that's how I get that, right? So I'm looking in the first row, first column for each place, right? So first row, first column of A, or rather 3A, first row, first column for B. That's going to be my first row, first column for the resulting matrix. So in the next space over, I'm going to get 12 minus 0. So again, looking at first row, second column. So I'm here, here, and that brings me here. And I'm not going to highlight a color for each term, but hopefully you're kind of getting the picture here. So let's continue. So in the first row, third column, I'm going to get 6 minus -3. And now I can proceed to the second row where I get 6 minus 12, minus 6, minus -10. And just to highlight again our location. So that was second row, second column, second row, second column, it better go in the second row and second column of my resulting matrix. All right, so moving forward again, 9 minus negative 5. And then in my third and final row, 9 minus 1, 3 minus 10, and 12 minus negative 1. So now I can just go ahead and simplify this. So up first row, first column, I get 5, followed by 12, then 9, negative 6, 4, 14, 8, negative 7, and 13. So this, since I've gone so far away, this was 3a minus b. The last operation we're asked to perform is 2c plus a. Well, the dimension of c is 2 by 3. And a is 3 by 3. Because their dimensions are not equal, you cannot add these. So next we're going to talk about when two matrices are equal. So two matrices are said to be equal when every entry in A is equal to every entry in B in terms of position. So what I mean to say by that is, for this, X needs to equal 0. Right? They need to match up position by position. And notice the rest of the row, 1, 2, 3, is the same in both A and B. So I'll just let this guy be. We can call this guy A, and we can call this guy B. So we're good for 1, 2, 3. And then the next one, it better be the case that this value matches this value. So that says that Y needs to equal 11. And notice the rest of the row, 10, 11, 12. Oh, I made a boo-boo. I need to fix that. Apologies. So this was supposed to be... I knew there was a mistake on my horizon. So you should definitely make this correction in your notes. Sorry. So this needs to be 12 and 13. Okay, much better. So now we can see that these things are equal. Okay, cool. And then in the last row, it needs to be the case that in the third row, third column, these also need to be equal. So I would get that Z equals 11. Nope. Z equals 102. Right, so they just need to match location by location. Let's do a little bit more complicated version of this. Let's look at example number 2. So here we're going to get that 3 minus x has to equal 2x. So that's coming from here. We also know that z squared minus 16 needs to equal 0. And we have one final equation, which is going to be that 3y plus 10 needs to equal 4.